Volumes of revolution, the washer method. We will focus on rotating about horizontal lines y equals a, or with respect to x. Objectives. By the end of this lesson, you should be able to identify the region being rotated, ensure the axis of rotation is a horizontal line y equals a, find the limits of integration, these should be x values, determine if you will need the disk or washer method. If washer method is needed, find the inner and outer radius, and set up the integral or integrals with respect to x needed to find the volume of the solid. Let's begin by trying to imagine rotating this shaded region around the x-axis. Try to visualize what this three-dimensional solid looks like. So now we're rotating this region here that's between the two curves f of x and g of x on the interval from a to b. So imagine taking this region and rotating it around the x-axis. This figure was maybe a bit trickier to think about that rotation. So this here was the region we were trying to rotate, and on the far right, this is what the solid would eventually look like. So notice that the shape of a cross-section is this time a washer. So if you're not familiar with tools, maybe you don't know what a washer looks like, but basically a washer looks like a circle but with another circle carved into it. So the last method was called the disk method because a circle looks like a disk. This is called the washer method because a washer looks like a circle with a circle carved out of it. So rotating this region about the x-axis is going to leave us with a carved out center. So over here we can sort of see this carved out middle inside, which on a cross section results in a hole in the middle of it in the form of a circle. Alright, so let's formalize the washer method where cross sections are perpendicular to the x-axis. We're going to need f of x and g of x to be continuous. F of x is going to need to be above or equal to g of x, and both of these functions need to be positive or equal to 0 on the x interval from a to b. Then the volume obtained by rotating the region between the graphs about the x-axis is given by, so our volume formula is going to extend from a to b, and then I want to focus on this first line for a minute. So I have pi times the big radius squared minus pi times the smaller radius squared. So I want to think about that. Let's think about one individual cross section for a second. So this is one cross section, this is one washer. So if I were interested in finding the area of this washer, so this blue shaded region here, what I could do is think about taking the area of the bigger circle with the bigger radius, we'll call that big R, and that would tell us the area of the entire thing. And if I just wanted this blue ring, I would need to subtract the smaller area with the radius little r. So I would do pi r squared, big R squared, minus pi times little r squared. So that's what this is saying. I'm going to add up the integral, right? Integrals is to add up a bunch of things. So I'm going to add up all of the cross sections from a to b of the bigger circle, and then I'm going to subtract the smaller circle's area. So every single time. So the big radius minus the small radius. So in function notation, I'm going to take big R of x squared minus little r of x squared. And since pi was in both of these, I could factor it out of both, and then I could factor out any constant out of the integral. So big R of x is going to end up being top minus bottom. So I'm going to need to find a top and bottom to the big radius and subtract them. And remember to square that. And then minus the top minus the bottom of the little radius. And remember to square that. So if we're rotating around the x-axis, the bottom function is always going to be 0. So we're going to have f of x minus 0 squared, or really just f of x squared, minus g of x squared dx. So this is if we are rotating a region that's going to create a washer about the x-axis. But we'll see that it's possible to rotate around another horizontal line other than the x-axis. So again, to summarize, big R of x is the outer or the bigger radius of the circular cross-section, and little r of x is the inner or the smaller radius at different values x. So it is possible to rotate a region about a horizontal or a vertical line other than the x-axis or the y-axis. The horizontal or vertical line we rotate about is called the axis of rotation. So we're going to stick to rotating around horizontal lines for now, but pretty soon we're going to be rotating regions around vertical lines as well. But the line we rotate around is formally called the axis of rotation. Alright, when it comes to the washer method and when we start rotating around lines other than the x-axis, things start to get a little tricky. So I have my own strategy for teaching this. So this is what I'm going to recommend you use when the washer method is needed. So when we think about rotating a particular region, if we can see that there's going to be a little area or a little region that's going to be sliced out of the inside, we know we need the washer method. And when that happens, first, I want you to start by drawing a line from the axis of rotation to the function that's furthest away from the axis of rotation and label that line big R. Then draw a line from the axis of rotation to the function that's closest to the axis of rotation and label that little r. And then find the length of each line, big R and little r, using the top minus bottom formula. So note that sometimes this gets tricky because you may have to split into two different integrals if the top and bottom functions are different, or flip as you move from x equals a to x equals b. So this is just going to come with a lot of practice and really being really neat with your graphs and the labeling of the functions. Alright, let's start with our first example. So find the volume of the solid obtained by rotating the area between y equals x squared plus 4 and y equals 2 over the interval from 1 to 3 about the x-axis. So here the graphs have been drawn for us. So we have x squared plus 4 and y equals 2, so the blue lines are the graphs. And we want to rotate the area over the interval from 1 to 3 about the x-axis. So we're rotating here around the x-axis. So as we can see, there's this little gap between the region and the axis of rotation. So when we rotate this, we know we're going to have to carve out a little section, so we're going to need the washer method. Now, once you establish you're going to need the washer method, again, I advise that you start from the axis of rotation, so put your pencil on the axis of rotation, and draw a line to the function, a straight line from the function that is furthest away. So my two options here, the two functions, are y equals 2 and y equals x squared plus 4. So the one that's furthest away is x squared plus 4. So I try to draw it straight. It should be a perfectly vertical line. And I'm going to go ahead and label that big R. So that's my big radius. And now I'll use a different color. I need to start from the axis of rotation again, so put my pencil on it, and then go to the closer function. So the closer function is y equals 2. And I'm going to label that little r. So now my generic volume formula is pi times the integral from, well, my two values on the x-axis of importance are x equals 1 and x equals 3. And then in general, what I need is big R of x quantity squared minus little r of x quantity squared. So big R of x can be found by doing top minus bottom. So the top function is x squared plus 4. So here I have x squared plus 4. And then the bottom function of r, so we're looking at this capital R, the blue line that I've drawn. The bottom of the line is hitting the x-axis, which is y equals 0. So it's x squared plus 4 minus 0. So I'm not going to write that because we wouldn't write minus 0. And then squared minus the little radius squared. So the little radius, the top of the little radius is y equals 2. And the bottom of the little radius is on the x-axis, which is y equals 0. So 2 minus 0 squared dx. So this is the volume, the formula needed to find the volume of rotating this region around the x-axis. So we can do just a little bit of simplifying here. So I'll do pi times the integral from 1 to 3. And then if I were to solve this by hand, I would have to distribute x squared plus 4 times x squared plus 4. Here I can go ahead and just write minus 4. So I have 2 squared, so that's 4 dx. So this sets up the integral to find the volume of the solid when I rotate this region about the x-axis. For the next example, calculate the volume V of the solid obtained by rotating the area under y equals x squared and above the x-axis about the line y equals -2 for x values between 0 and 3. So let's go ahead and try to draw an accurate graph that depicts what's happening. So here's my xy plane. I want the graph of y equals x squared. So I'm really concerned with things between x values of 0 and 3. So on my x-axis, I'm going to go ahead and mark 0 and 3. So x squared is a parabola. It's going to look something like this. And I want the area under y equals x squared above the x-axis and between 0 and 3. So let me go ahead and draw a straight line up so I can highlight the region of interest. So I'm rotating this region and I want to be above the x-axis. So this little sort of triangular region is the one that I'm rotating about the line y equals -2. So -2 is a horizontal line, and it is down below the x-axis, so y equals -2. So this is the line that I'm rotating about, y equals -2. So we can see that there's this gap between the region that we're trying to rotate and the line we're trying to rotate around. So there's going to be this part that I'm carving out, so I need the washer method. So now here's where I want to go from the axis of rotation. So the axis of rotation is y equals -2, so I put my pencil on that axis of rotation and I go to the function that's furthest away. So my options here, I should have labeled them. So y equals x squared is this curve, and then this horizontal line here is y equals 0. So those are the two functions that I'm dealing with. So if I go from the axis of rotation to the furthest away function, that would be y equals x squared. So that is my big R. Then I would go from the axis of rotation to the closer function. So the closer function being the x-axis, being y equals 0. So notice we were given the x-axis as a bound, but they didn't specifically tell us y equals 0. We had to gather that from the fact that the x-axis is equivalent to y equals 0. So now this green line is little r. So when I set up my integral now, my volume formula in general is pi the integral from, on the x-axis my values are 0 and 3. So x equals 0, x equals 3. And then I want to input my big radius and then square it, and then subtract my little radius as a function of x and square that dx. So I need my big radius and my little radius. Well, I have my big radius drawn, but I need to write it as a function of x by doing top minus bottom. So the top function is x squared, and now the bottom function is no longer 0. We go all the way down to -2. So we have x squared minus -2. Then I need to subtract little r of x. So little r of x is top minus bottom. So the top of little r of x is 0. Minus the bottom of little r of x is -2. So if I were to want to simplify this at this point, I'd get pi times the integral from 0 to 3 of x squared plus 2 squared minus, and here I have minus a negative, so I have plus 2 squared, positive 2 squared dx, and these are being subtracted here. So if I wanted, I could rewrite this and square the 2, so I'd get minus 4. But this is the integral that's going to find the volume of revolution rotating this red outlined region around the line y equals -2. Alright, moving on. Calculate the volume V of the solid obtained by rotating the region between y equals the square root of x, y equals 1, and the y-axis about the line y equals 3. Alright, so let's try to draw the region. And sometimes drawing the region can be a lot of the battle. So we have to make sure that we can graph all of these functions without a calculator. So y equals the square root of x is one of our bounding functions. So let's label it y equals radical x. Y equals 1, so that is a horizontal line at 1 on the y-axis. So there's 1. So here's my line y equals 1. And the y-axis. So the y-axis has already been drawn for us. Here it is right here. So the region that intersects all of these is this one right here. So, whoops. There's my region of intersection. So this is what we're rotating around the line or about the line y equals 3. So that is way up here. Let me go ahead and draw that as a horizontal line. So this is what I'm rotating around. So this is my axis of rotation. Alright, so just so that we've written our functions way over here, but this ended up being the region. So just to keep my functions straight, I'm going to go ahead and write next to this little curve, I'm going to put y equals radical x so that I don't forget that's this curve. And then right next to this part of the line, I'm going to go ahead and write y equals 1. So I don't forget that that's the line y equals 1 and this curve is y equals radical x. So now I'm going to need to find my big radius and my little radius. So start from the axis of rotation when where now that axis of rotation is above the region in question, which is fine. That strategy that I gave ends up being really useful regardless of where the axis of rotation is. So it works the same way. I start from the axis of rotation and go to the function that's furthest away. So the function that's furthest away in this case is y equals radical x. So that is my big radius. And now my little radius, I'm going to go from the axis of rotation to the closer function in that region, and that's little r. So now if I set up my integral, I have pi needs to be on the outside, whoops, from x equals. Alright, so finding the limits of integration now are values from the x-axis. So we start at x equals 0, but now the question is, well, what's this value right here? So y equals radical x, if I substitute in 1, I get out 1. So I know this coordinate point right here is 1, 1. So that means the other x value I'm concerned with is 1. So 0, 1 are the numbers I need to form my limits of integration. And my big radius squared, and I will do it in purple to match my big radius, is top minus bottom. So the top being 3. So this is the line y equals 3. So 3 minus the bottom function is rad x. So it's my big radius squared. So here's my r of x. And then I need to subtract my little r of x and square it. So little r is top minus bottom, so 3 minus 1. So 3 minus 1 quantity squared, and then dx. And if I were to do just a little bit of simplifying, I would get pi times the integral from 0 to 1. So 3 minus radical x squared. Once again, do not be tempted. This squared does not distribute, so this is not 9 minus x. That doesn't work. And then minus, so this is 2 squared, so minus 4 dx. And then this is the setup. We could use our calculator to evaluate this integral. The setup is clearly the hardest part, so finding the correct big R of x and little r of x and squaring each one, and then definitely not forgetting the pi. Alright, next example. Find the volume of the solid obtained by rotating the area between y equals x squared plus 2 and y equals 4 minus x squared about the line y equals negative 3. So the graphs have been given to us. Although these are two basic functions, you would need to know how to graph without a calculator. So f of x is x squared plus 2, so that is this upward facing parabola here. And then g of x is 4 minus x squared, that's this downward facing parabola here. And we want to rotate around the line y equals negative 3. So here's my axis of rotation. It's below the region, and just for some extra visuals, here is an example of what one of the cross sections would look like. And then here's an example of the completed solid. Alright, so I need to find my big radius, so I'm going to start from my axis of rotation and go to the furthest away function. So here, if I start at the axis and I go up to the furthest away function, that function is 4 minus x squared. So please don't be confused and think that the top one is just the one that's currently labeled further up. So that's why sometimes it's helpful if right next to the function we write its label, we write its name. So this one up here is 4 minus x squared, whereas this bottom curve right here that we're going to hit when we go to the lowest function, that one is x squared plus 2. So this is my big radius, and then my small radius from the axis of rotation to the closer function, that is little r. So now we can go ahead and set up our integral. So I have pi times the integral from, I'm being told here that the limits of integration are my points of intersection that have been given. So those two x values go from -1 to 1. But we could, of course, find them by setting these two functions equal to each other, and we should know how to do that by now. So I'm going from -1 to +1, and then big R is top minus bottom. So 4 minus x squared, so that's top, minus the bottom is -3. So minus -3 squared. So there's big R squared, minus, and then little r is top minus bottom, so x squared plus 2, minus the bottom is -3 squared dx. So I don't know that I'd go past too much more simplifying here. Maybe from -1 to 1 of 4 minus x squared plus 3 squared minus x squared, and then here plus 5 squared dx. Maybe inside here we could go 7 minus x squared, but I wouldn't really do too much simplifying past that. We can go ahead and just enter it into our calculator from here. Another thing to talk about is that if we want, we could use symmetry here. What we could have done is, because going from 0 to 1 is the same volume as going from -1 to 0, that rotation around the same line, -3, we could also have expressed this as 2 times pi of the integral from 0 to 1 of the same exact integrand. So I'll write that as 7 minus x squared squared, and then minus x squared plus 5 squared dx. So that is another possibility. Not to say that it makes it any easier, any harder, but we should be able to recognize that symmetry. So we're doubling, rotating just this, that little region, instead of finding the whole thing. But again, not to say that it's any easier, but it's possible this could be a multiple choice question on the AP exam, and this here may be an answer. And it might not pop out to you because you see the 2 in front, but you know, that's possible using symmetry to find the volumes. Alright, so now let's find the volume of the solid obtained by rotating the area between 9 minus x squared and y equals 12 on the interval from 0 to 3. First about the line y equals 12, and then about the line y equals 15. So there's two different problems happening here. So I want the area between 9 minus x squared, so that would be this bottom curve here. So I'm going to label it close to it. So this bottom curve is 9 minus x squared, and y equals 12. So it's just the horizontal line at 12 on the interval from 0 to 3. So this pink region is the one we want to rotate. And first we want to rotate around y equals 12. So we're rotating around this horizontal line that borders the region that we're going to rotate. So if I rotate around this line, I actually will not end up needing a washer method here because I have no gap in between that I need to carve out. So this is an image of the solid, and notice there's no part that's carved out. It's a solid object entirely without any inside part missing. So for part B, I actually only need the disk method. So I need the radius of each of my disks. So if I think about drawing myself a little disk, doesn't look like a circle, but here's one of my circles. So here's my radius here, which can be found by doing just top minus bottom. So my volume formula for, let's call it part A, is pi times the integral from x equals 0 to x equals 3 of just the one solitary radius, top minus bottom, so that's 12, minus the bottom function is 9 minus x squared. So here's where we want to be really careful. It's 12 minus the quantity, 9 minus x squared, squared. So a lot of this, again, boils down to the setup, and the question or the answer, the integrand, would not be correct if there were not parentheses here, because this negative would distribute. So I would need to distribute the negative to both, so I'd have 12 minus 9, so that would give me 3, and then plus x squared squared as my integrand for part A, or rotating around the line y equals 12. So let's just clarify, if I were rotating this region around the x-axis, now I would definitely need a washer method, because I have this big gap here. The entire region doesn't border the axis of rotation, just this one point sort of touches the axis of rotation, but I'd still have to carve out this inside part. But since I was rotating around 12, I was bordering the axis of rotation entirely, so there's nothing to carve out. It's just a disk method. And now the next part is to rotate around the line y equals negative 15. So I'm going to go ahead and erase this, because now we're going to draw our axis of rotation, which is above the region, at 15. So this is y equals 15. So my big radius goes from the axis of rotation to the further away function. My little radius goes from the axis of rotation to the closer function. So now if we set up, let's call it part B, we have pi times the integral from still 0 to 3. My big radius, we'll go ahead and do in the same color in blue, is going to be the top function, which is 15, minus the bottom function, 9 minus x squared, all squared. So that's the big radius squared, and then we're going to need to subtract my little radius squared. So top minus bottom here is 15 minus 12 squared dx. So this is the setup that finds the volume of the solid obtained by rotating this region now around this line y equals 15. Alright, and just to go over a couple of final reminders, you should be able to sketch all of the graphs that we went over without the use of a calculator. If necessary, you would need to find points of intersection without the use of a calculator. Once you set up the integral correctly, you can use your calculator to evaluate the integral. So most of the points come from the setup. And then when you provide your answer from the calculator, either round or truncate your final answer to 3 places past the decimal, the thousandths place. So leave your answer like 23.083. Or you can leave your answer exact as 22 over 3 pi. But you wouldn't want to leave your answer. It's bad form to leave your answer in a combination of an approximation and an exact value. So you wouldn't want to leave your answer as 7.333 times pi. So you would just want to multiply this exact answer that you got from your calculator. You want to multiply that by pi and rather leave your answer like this. So these two are your options. You don't really ever want to leave your answer like this.